In this video, I want to take a look at a situation where you have two different sets of vectors that when you take the span of each set, you end up with the same space, and see what we can say about that situation. So here's a quick example. In R3, let's take the vector v1 to be the vector 1, 2, 0, and v2 for negative 2, 0. I'm going to take those together as a set, as you'll see here, and then take the span. Likewise, I got W1 and W2, and W1 is just 1, 0, 0, and W2 is 0, 1, 0. Look at the span of both of those. Well, the thing I notice about all of them is that the z-coordinate is 0. This one I think is probably pretty clear that the span of W1 and W2 is the xy plane. Right? Every point on the plane, A comma B, could be written as A times W1 plus B times W2. Right? Actually, sorry, it's not A comma B, is it? It's A comma B comma 0 because we're in R3. Anyway, it's still A times W1 plus B times W2. Right? Less obvious is that the span of these two vectors, V1 and V2, is also the xy plane where z equals 0. Right? Notice that it's probably pretty clear that you can write V1 as 1 times W1 plus 2 times W2. That's what we already said, that everything can quickly be written as a linear combination of those two. V2, this should say V2 right here. In fact, I probably got a pencil and I can turn that into a 2. There we go. V2 is, well, 4 times W1 minus 2 times W2. So I can write each of these two vectors as a linear combination of those two vectors. Likewise, look what happens here. W1, I claim, is 1/5 V1 plus 1/5 V2. So if I take this and multiply it by a fifth, that would be 1/5, 2/5, 0, and this would be 4/5 minus 2/5, 0, and 1/5 plus 4/5 is 1, there you go, and 2/5 minus 2/5 is 0, there you go. So W1 is that linear combination of those two. Likewise, W2 is this linear combination of V1 and V2, 2/5 V1 minus 1/10 V2. So what I have here is I have that both of these sets, this pair and that pair, when you take the span of them, you end up with the same space. You end up in this case with the xy plane. Also, each vector can be written as a linear combination of the others, the ones in the other set. And this is not a coincidence. One of the things that I should point out here is that in both of these, I have just two vectors, but it doesn't matter. Sometimes you might have 3 vectors in one of your sets and 17 vectors in the other set. But when you take the span of them, if you end up with the same space, it turns out that there's a very close relationship between the 3 vectors and the 17 vectors. And this theorem is what that relationship is. So if you're given two sets, S1 is this set, V1, V2 up to Vn, and S2 is this set, W1, W2 up to Wm, and all of this is in some vector space V, then the following are equivalent. Before we look at that, let me just reiterate here, point out that these sets, S1 and S2, are finite. They have finitely many elements in it. This one has n vectors in it, this one has m vectors in it. They're not infinitely many, there's finitely many in each, so it's essentially a small number of vectors. Even numbers like a billion are small compared to infinity. Okay, so finite numbers of vectors. Then the following statements are equivalent, that the span of the two sets are equal to each other. Span of S1 is equal to span of S2. That's equivalent to saying that every element of S1, every one of these vectors, can be written as a linear combination of all these vectors and the other way around. So these vectors can be written as a linear combination of those. To say that they're equivalent is to say it's an if and only if. So to prove it, you got to say if this statement is true, then this statement is true, and then start all over again with if this statement is true, then this statement is true. You got to prove that if and only if means you got to do if then in both directions. Now certainly, if the span of this set is the span of that set, each one of these vectors is in the span of themselves, because v1 is in there because it would be 1 times v1 plus 0 times all these other things. So v1 is in the span of S1, and if the span of S1 is the same as the span of S2, then v1 is in the span of S2, and the span of S2 is by definition all the linear combinations of the w's. So v1 has to be a linear combination of the w's, likewise for v2 and so on. And likewise in the other direction, each one of these is in the span of S2, but if the span of S2 is the same as the span of S1, then each one of these is a linear combination of those. So the proof of 1 implies 2 is pretty straightforward. Okay. The proof going the other way, say, assume you know that every one of the v's is a linear combination of the w's, and that every one of the w's is a linear combination of the v's, then you have to show that these two sets are equal. And the way we show that two sets are equal is to essentially show that each one is a subset of the other one. So I'd have to take something in this set, in the span of S2, and show that it's in the span of S1. And then I'd have to take something, some arbitrary thing in the span of S1, and show it's in the span of S2. So going this direction, assuming 2, trying to show 1, actually in itself has an if and only if, because the statement of that two sets are equal is like an if and only if, that you have to show containment in both directions. And the way you would do that, right? Let's say we take something from the span of S1, right? So let's let V be some linear combination, A1, V1 plus, and so on up to AN, VN. Right? But I'm given that if I'm trying to show that 2 implies 1, I'm assuming that I know 2 is true. So I know that all of the V's are linear combinations of the W's. So what I can do is I can replace each one of these V's as whatever linear combination it is. So this one would be B1, W1 plus all the way up to BMWN, right? And then the next V can be replaced by a bunch of some linear combination of W's. And this last one would be some linear combination of W's. Something, let's say, C1 to Cn. Actually, M. There's M of them. And then what you have, you've changed all the V's into W's, and you can collect some like terms. So collect all the W1s together, collect all the W2s together, all up to Wm, and you've got a linear combination of the W's. So anything that's in the span of S1, so anything that can be written as a linear combination of V's could then be written as a linear combination of W's, because all the V's are linear combinations of the W's. Likewise, anything in the span of S2 is a linear combination of the W's, but if each W is a linear combination of the V's, then you've got this big linear combination of V's, and you're in the span of S1. Okay, so, and notice the numbers here are different. There's a different number. There might be the same number, but they might be different. As long as you know that every element of one set can be written as a linear combination of the other, and the other way around, then the two spans are equal to each other. Okay. Well, there you go.